It's like this is our void space. Yeah. All right. Hello, everyone. Let's get started with talking about P and NP. It was one of my favorite things in the class. I hope it's one of your favorite things. If it's not, hopefully you'll like it a little more after today or be less scared of it or something. And so the goal today, we're just gonna do some practice, making sure that it's very clear, like, you know, what is NP, how to show things are in NP, and then like doing our carp reductions and mapping reductions and getting practice with those. And then getting like, you know, the idea of like being able to look at a reduction and know like what are the types of things that you should try, and hopefully one of them will work out, and then like showing that it works out and not forgetting any of the small detail things that hopefully we also won't forget, but we would take off points if you forgot it on the midterm. And so, yeah, let's get started with a quick warm up, just like a review of some CYU type things. The first warm up question. Let's see. Is self-accepts accepts NP complete? Ooh, and recall, NP complete means it's NP hard and it's in NP. If we ask you to show something is NP complete, you have to show it's NP hard and it's in NP. Then someone have an answer for me. Is self-accepts NP complete? Why? Oh, and I guess we should recall what self-accepts is maybe. This is the thing. Does a Turing machine M accept its own encoding? Anyone? Okay, well, presumably, this thing is undecidable, right? So probably it's not an NP, right? Because we know that, like, I guess one good heuristic is everything in NP is decidable. This is a good thing to recall. And we saw in the textbook that like NP is like a subset of like the languages that can be solved in exponential time, right? And this thing is undecidable. So in particular, we can't like decide it in exponential time. But another like justification, something that can be like a little confusing to people is like, oh, well, can't I just have a verifier where like I'm given like a Turing machine M and then like my like a number K, and then I like accept if M accepts in K iterations, or M of M. And reject otherwise, right? And this would run in polynomial time with respect to the inputs, right? But recall that a verifier requires that we need like the size of K to be less than or equal to size of M to the K for like some fixed constant K. But these Turing machines can take like arbitrarily long to halt on their own input, right? So this number K, if my Turing machine has, you know, or if my Turing machine takes like 5 bits to encode it, K could still be like a Google, and there's no like polynomial upper bound for that. So this verifier like does not satisfy this. It doesn't satisfy this. Is this clear to everyone like why this like doesn't work? This is just like a good thing to keep in mind, why it's important that we actually add the restriction of like a polynomial upper bound on our like certificate. Cool. Okay, the second one. This CYU is also a good one to recall. P equals NP implies co-NP equals NP. And so I guess this is supposed to be a you tell me this, but I just wrote down that it's true because it was on a CYU. But basically, the important thing to remember here is that P is closed under complement, right? And it's also closed under a lot of things like intersection and union. So like P is equal to like co-P, which is like the things not in P, which means that tells me that P is equal to NP, or sorry, NP is equal to P, which is equal to co-P, which is equal to co-NP. And a quick thing to remember is that co-NP is not the set of all languages that are not in NP, right? Co-NP is not the set, is not equal to power set of sigma star minus NP, right? We know co-NP is actually equal to sigma star minus L, or L and NP. This is what it is equal to. If there's a question that involves writing out what co-NP is and using like definitions, it's not this, it's this. It's the things where our verifier, it's the things that our language would, or like a decider for our language would reject. It's not like everything that's not in NP. Cool. Last one, recalling the closure properties of mapping things. So is it true that if A less than or equal to B and B less than or equal to MPC, then is A less than or equal to MPC? Someone want to tell me if this is true and why, or why not? Any takers? Yeah. Yeah, so the observation is if we just follow the definitions here, this means that like there's a function f such that x is in A, if and only if f of x is in B. And then also this means that like x is in B, if and only if h of x is in C. And so if I just combine, if I like follow this chain of definitions here, that tells me that like x is in A, if and only if f h of f of x is in C. And so this function h of f of x has the property that x is in A, if and only if x is in C. And also because f is polytime and h is polytime, that tells us that h of f of x is polytime, and then we're happy. So car productions are good because they have this closure property, which is nice. Is this clear why this works? Cool. So yeah, that was a bit of a warm-up, recalling some definitions, like some minute detail type things. Always justifying things are polytime is good. Cool. So now let's move on to practice with verifiers. Practicing verifier. And so if we ever tell you a question that it looks like show blah is in NP, what you should always do is write down something of the form, like def v x u, and then something where v, right, instead of blah, let me write L. So yeah, we want to come up with a verifier such that like, you know, there exists certificate u size of u less than or equal to x to the k such that v x u accepts, and we say like x is in L if and only if x is in L if and only if that's true, right? So we want to come up with a verifier of this, and v is polytime. And so justifying all of these, in particular, justifying this and justifying that are important. Justifying why its polytime is important, or why its U is polylength is important, because otherwise self-accepts as an NP, which is bad. And justifying that its polytime is good. And it's polytime like with respect to U and X. So like if U is really long, if U is like long but X is short, then it's polytime with respect to U. But we know U is like polynomially sized in X. So polynomially sized in U is also polynomially sized in X. Anyway, all that said, let's make a verifier for this language. So given S and T in sigma star, does there exist a sequence of at most A insertions or deletions in that make S equal to T. So for example, if, and let's say sigma is like 0, 1 for simplicity. So for example, if S is equal to 0 and T is equal to 1, 1, then it's not the case that there's 0 insertions that make these equal. It's not the case that there's 1 insertion that makes them equal. But it is the case it's also not the case that 2 make them equal, but 3 insertions or deletions make them equal, right? Because I can do like delete 0, like insert 1, and insert 1, and then I get 1, 1, and now they're equal. So does anyone want to tell me what my verifier might look like for this language? I'll call this L. L equals S T K. Bless you. Anyone want to tell me my verifier? Also, note that I was very careful here, and like this is something you should be careful about, is making sure like your verifier accepts like the correct type of thing as its input, right? Like something that you can do is say, oh, I'm gonna make my verifier like take in strings like S and T and then a certificate U. But remember, this is ST and like K, for like K is some number. So you need to make sure, like, don't forget, like, this is a very easy thing to like forget to do, and then all of a sudden the problem becomes a lot harder. Like, once you know what your input looks like if it's a graph and a number, or is it like 2 strings and a number, just write down, replace X with like the type of the input, just to make your life easier. Anyone want to tell me what my verifier is going to be? What it's going to do? Yeah.
So you would be like a sequence of K insertions or deletions, and then you'd like do those insertions and deletions on S. And
Yeah.
Then
Yeah, exactly. Nice. So the first thing is making sure that U actually is of the correct form. So it was, as said, if U is not a sequence of at most K insertions / deletions, reject. And now if we made it past that point, we know that U is a sequence of at most K insertions and deletions. So now we can do the insertions / deletions U specifies, and then on S, and then except if S equals T. And so this is a good thing to point out, is that like this is very abstract, right? Like I don't know, I didn't actually specify like what U has to look like what is U just the word insert here, insert there, delete there. I don't really care what that is, right? Like this is what we look for is like, this is like a good enough specification of what you're thinking to do, that it's clear that someone could, like a reasonable human being or algorithm or something could implement this in polynomial time. So like, don't get caught up in like the nitty gritty details of exactly what U looks like or that. But as long as like something like this, where you literally go through and for each property of the language, like make sure it satisfies that property and accept if it satisfies all of them and reject if it doesn't, that's okay. And so now we can go ahead and justify that this is a valid verifier. So first we can say V is poly time because I can insert / delete an S quickly. And maybe I just say this is like O of n time or something, and like O of n per operation. I don't know. You can like honestly make up the time complexities as long as it's pretty reasonable. And I do this k times, so it's like, you know, it's like O of n times k, which is polynomial to the length of the input, right? Because this is polynomial to the length of the input, and then also I can say like, you know, U if X is in the language. So now this is the part where we need to justify that if X is in the language, then there exists a certificate of poly length that will make it accept. So I can say if X is in L, there exists, or sorry, X equals S T K is in L, then, you know, there exists the sequence of insertions that of inserts / deletes to make S equal T. So U equals the encoding of that thing, that sequence. Works. And I can say, and has like size, I don't know, less than or equal to like size of S squared or something. You know, it's like I can encode this if like it's like a sequence of insertions and I just say where it is in S and like what it does. I can make it small, right? You can be a bit hand wavy about like, you know, how big things actually are. The point is like they're small. And then now I can say if X is not an L, then any sequence of insertions that / deletions will fail. So I will reject, and I will reject on any U. And that's a sufficient proof that this is a verifier. I'm not writing out the second part, but just if X not an L, ... Yeah.
So for you, I know that like in the past when I was doing like writing through the journal, we kind of had like in the type check where we would say like
Yeah.
when we would say that to be equal to like I would never why can't we do that here?
Because you could like it, like when we do those type checks, those are normally of the form like if M is not a valid encoding of a Turing machine reject or something. But U, for example, could be a sequence of insertions or deletions, but it depends on like what K is, whether or not it's a valid sequence that most K insertions or deletions. So it depends on our input, like the type check of U depends on our input here. So we would want to include that inside of our verifier.
Okay.
Mm-hmm. Yep. Yeah, that's a good point. Like for these sorts of things, like we could also like say, you know, V of X, whatever, but we can just like for our verifiers, we can always assume that our input will type check. Like so we can always assume X will have the form like S T K, but we can't really assume that on U. So we always need to make sure U type checks. Cool. So now we can move on to some reductions. Okay, these ones will be like baby reductions, and then we'll go on to like adult reductions. Okay. So I just want to emphasize, like when I look at reductions, I kind of like classifying them into like 3 categories. So I have like 3 categories of what reductions look like. Of reductions. So the first category is like this like problem is okay. So I want to show like A reduces to B. So my first type of reductions I like want to look for is B like exactly the same, like basically exactly the same thing as A. slash like a small reword. So like, an example of this class of reduction could be like, for example, 3 coloring is less than or equal to K coloring. Because if I can solve K coloring, then, I can solve 3 coloring because I just call K color on 3. There's less obvious forms of these types of reductions. Like sometimes it's not gonna be this obvious, but there are times where like your problem is just exactly the instance of the other problem, but you just change the word a little. Another type of reduction is like do like a transformation on the whole input. The whole input. So like, for example, we saw in recitation, like the click less than or equal to like the 2 clicks problem, or sorry, 2 clicks problem. Where my transformed input is I just take my input and then I duplicate it, right? Or maybe my transformation could be I take my input, it's a graph, and I like look at its complement or something. And I do whatever I do on the entire input, right? And then like kind of the third category of reduction is like for every like X in my input, do Y, right? And so an example of this is like hotspot. Like a lot of people did hotspot by saying it's like let's say we go to vertex cover. Woo, yeah, hotspot. So like you said for every vertex in my graph, like just add like a triangle that like makes it complete. And like I don't know if you have other types of reductions that you think will often appear, but these are like the 3 categories that I like to classify them into. And like I can't say like for some X in my input or like because the reason why I phrase it as like for every X in my input do Y is because like if I want to reduce like hotspot to vertex cover, I don't know like where my vertex cover. Oh, wait, I said vertex cover, but I wrote this wrong way. My bad. Don't mess up writing which way the reduction goes. So like I couldn't say like, oh, if this guy is in a vertex cover of size K, then do something because it's not polynomial time to determine like where where my vertex cover is going to be. So like I can't say if it's like in a vertex cover, do this. I have to say for everything my input do something, and then show that the thing I did like has the nice transformation property of my output. So those are my 3 types of reductions, and we'll see the different types of reductions, and they'll all fall into one of these categories. So try it. Yeah, I don't know. That's helpful for me to think about. Anyway, so now let's move on to our reductions. So okay, our first reduction we're going to look at is, or I guess reductions slash showing NP hardness. Because whenever you're asked to show something is NP hard, you always want to reduce an NP hard problem to that thing. So first problem is we're going to let L be the language of graphs G1 and G2 graphs, and G1 contains a copy of G2. And we want to show this language is NP hard. So for example, if G1 is like a square and G2 is like a line, and G1 contains a copy of G2. G1 also contains this guy. G1 does not contain a triangle because there's no like way I could put a triangle in here. So I said these are baby reductions in the sense that what I want to do or what I want to reduce from might be a little easy. So does anyone have an idea with that hint of what I might want to reduce from? Yeah, wow. And what would I do?
Just put you on the original graph and G2 size K.
Nice, exactly. So yeah, this falls into the first category of questions of is B exactly the same question as A, which is this language L. Okay, so I want to show that click reduces to L. And my algorithm is, so I'm going to define my mapping function where I take in a click and an input K. and sorry, and a number k, and then I could just return G and a click of size k. So I'm mapping instances of L of click to instances of L. Um, so now we can justify why this works. So I can just say, you know, GK, and yeah, GK is in click, and then it works, right? Yeah, it works. If it's not a click, there's no click of size k in here. I'm not going to justify this. We'll get to harder reductions later where we'll justify proofs of correctness. And it's also polytype. Hooray, I said the words. Any questions about this guy? Okay, another reduction. Let L be, okay, this one is gonna be graphs and a number such that G contains a cycle, or no, not a cycle, a polygon with k edges. And by a polygon, I mean a cycle, right? So for example, this graph here has a cycle of length 4, but not a polygon with 3 sides. But now this graph has a polygon with 3 sides and 4 sides. Does any, thank you. Anyone have any ideas of what I can do or reduce this to or from? And this is another thing. This is a baby reduction. Keep in mind the reduction problems we have. And maybe, yeah.
This is an answer, but are we gonna get like on homework 7, we had like that list of problems that are.
Yes, you'll get the list of NP hard problems on the exam.
Thanks.
Yeah. Cool. I don't want to ponder on this one too long. But maybe let's look at like the Hamiltonian cycle problem. We have bigger fish to fry. But let's keep in mind in our like little handy dandy list of reductions. This is one of the ones that we have is like NP hard. And recall, this is like, does there exist cycle of length size of V in G, which is like, you know, V, E. So given that I want to reduce from this, what is my reduction?
It's the same graph, just run Hamiltonian cycle.
Nice. Yeah. So L is just exactly Hamiltonian cycle. So I can do def F. So I'm mapping Hamiltonian cycle to L. So I give it a graph G, and then I just return G and like size of V, and G is equal to V E. Wow. They often these types of reductions, the ones I call the baby reductions are this one, but sometimes they're less straightforward than this. Like there might be a more complicated way in which like the two problems are actually the same. But yeah, that's always a good thing to look out for. When you look at a reduction, just keep in mind like the NP hard problems we have, and just see, is one of these problems like very, very similar to another one, or can I just like rephrase what I'm asking in terms of a different question? And yeah, reductions.
All right. So we're moving on to kind of more difficult reductions. Take like 10 seconds.
Oh, wait, oh, yeah, that's-
All right. All right. Okay, So Harrison started off by giving us kind of good tips on like the categories of reductions. So I'm gonna start off also by giving my couple of tips on reductions and stuff. First thing, this might be kind of stupid, but if you were trying to show A reduces to B, the way I kind of think about it is like, you know, the inequality sign is opening up towards the right. So like I kind of think of it as like A trying to like beat B. So like so in the Turing machine for A, like you're using Turing machine for B as a subroutine, right? So okay, if you think about it this way, you'll never forget. Like in 20 years, you'll another thing, carb reductions. We use carb reductions to show NP hardness, right? And the thing about carb reductions is that it's defined as A carb reduces to B if there exists a polytime computable function f such that x is in A if and only if f of x is in B, right? So to prove the carb reduction, what you do is give that function f and then show that it's polytime and also show this simplification. We refer to this as like forward direction, backward direction when you prove this bidirection null statement. The forward direction is pretty straightforward. You assume that x is in A and show that your function maps it to an instance in B. For the backward direction, commonly you can think of as like having two options. One option is like assume that f of x is in B and then get from there that the original A, x must have been from A. Another option is using the contrapositive of this and assuming that x doesn't equal, is not an A, implies your function should map to a known instance in B as well. So these two are the exact same thing, but sometimes one might be easier than the other. So just to think about, right? And we'll see today examples of both. Okay, let's do some questions. First problem that we have is called even subset sum. The way this is defined, we have given as input some sequence of numbers, A1 through AN, and then some target number, T. And then what we want to know is, does there exist some subset of the indices, right? This bracket N notation, such that for all I and S, A sub I is even, hence the name, and if you sum up all the indices in S, like the elements of it, does this equal the target? Right? So this is slightly different from the subset sum problem in that we have the additional constraint that A sub i's must be even. Does that make sense, everyone? All right, cool. And we want to do that even, I'm gonna read it like this, is NP hard. To do so, we want to reduce from a known NP hard language to even subset sum. Can someone tell me what we should reduce from? Not a trick question. Yes. Yeah, subset sum. Cool. Yeah. So basically, the way you can think about this is that input to the subset sum problem is similar, that you get a list, a sequence of numbers, and also a target. And we want to somehow like map this to maybe another sequence of numbers, another target for the even subset sum problem. Cool. So I'll let you think about that for like 15 seconds, how we can do this mapping. Would anyone like to volunteer an idea? Yeah.
We remove all odd indices from the set. There are a set of AIs, right?
Oh,
And then run subset sum on that.
so the question is that like the
No, that's not all indices, but like all odd values.
odd values.
Yeah.
I see. That's a good first idea. But the thing about like removing stuff from the original list of arrays is that if some of those happen to be part of the sum that makes a target, then we lose that, right, information. So yes, that would be a good idea. So another, like, usually a better way is to kind of add stuff or like modify stuff that we already have, other than removing stuff. So yeah. Let's have our function f take in that sequence of numbers and target t, and then simply just return 2 times a1, 2 times a2, etc., times an, and then 2 times t. And let's prove that this actually works. First, we do want to kind of make a statement that this does run in polytime. In the actual midterm, maybe I would say something like, oh, I'm just multiplying 2 to each number, which we can do polynomial time, and we do it once each number. So that is polynomial time, and it's fine. In terms of proof correctness, we want to do the 2 directions, right? First, the forward direction. I will try to completely write this out because it's kind of our first one. So first, assume that our input to the subset sum problem is in subset sum. Okay. What does this mean? Kind of definition, by definition of subset sum, this means that there exists some subset of indices such that if you add the elements up from those indices, that number equals the target, right? By definition. Okay. But then what does this also mean? Well, that means we can take that same subset of indices and basically, if we sum up 2 times ai's instead, then this should be equal to 2t. And that's just by math, right? And you should also know that 2 times ai's, these are all even, because 2 times any number is even. This is exactly kind of the definition that we're looking for in the even subset sum problem. So this implies that 2a1 dot 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 2an 2t is in even subset sum. Cool. Try to write this higher up. Now let's do the other direction. I will try to use let's say option 1 from what we talked about. So let's assume 2a1, 2an is in even subset sum. So what does this mean? Well, by definition, there exists some subset of indices such that I guess 2ai's are even. Sure, and if you sum them up, it should equal to 2t. And again, by math, this implies there exists that same subset of indices such that if you sum up only the ai's, this should equal t. So our original input must have been in subset sum. All right, 2 directions. You can do it using option 2 as well. I'll briefly talk about that. To do so, we're assuming that x is not in A, right? If we assume this is not in subset sum, that means like for all subsets of like indices, the sum of ai's does not equal the target. And again, you can get from here to saying that like sum of all the 2 ai's should equal 2t. And so our mapping should now be in ESS. Cool. Any questions about this problem? All right. So this one was a bit simple in that we kind of knew which language to reduce from, excuse me. But let's try an example where it's not as obvious as before. I'm going to define a new problem. It's called RV. What you're given is a set R of random variables. We'll call them like x1, x2, xn, and also some rational number R. Cool. And the question that we're trying to answer is, oh, and also, sorry, these random variables have the property that they're pretty simple. So all the xi's are defined to have value either 0 or value a fixed value like b sub I with the same probability. So they both like 50% chance either 0 or b sub I. Cool. And then let's just define for any like subset of bracket n, let's define this new random variable x sub s, which is basically the sum of the random variables where the indices are in S. Does that make sense? All right. And the question that we're trying to answer does there exist some xs such that its expected value is equal to any questions about this problem definition? So one thing different about this is that for this problem, we gave like an explicit language of what it looks like. Here, this is more like a decision problem format, right? But we know decision problems and languages are, they correspond. So let's write the corresponding like language for this. One thing we might have to think about is like, what is a reasonable like encoding of this problem instance, right? And I would argue that like only thing that you need to know is what these v sub i's are and this number r, right? Because the v sub i's uniquely define like what exactly the random variable x sub I is. So maybe some kind of encoding where you like list all the v sub i's and then r, that might be a reasonable encoding of this problem. And the condition is that like there exists some subset of indices such that the expected value of x sub s is equal to r. Cool. All right. Is it okay if I erase this side? Yeah. Okay. Now for this one, you might be thinking, oh, it's not very clear like what I should reduce this from. Because, well, it has like things about random variables, which we talked about in a different unit. So kind of what's going on here. So let's write down some like, a helpful tip is like writing down some observations that you have about problems, right? I would say that like first thing that comes to mind is that like, how do we know what this expected value is, right? And maybe more fundamentally, like what is the expected value of these like x sub i's? We know that the random variable x sub I is defined as, half probability of 0, half probability of b sub I. So can someone tell me what the expected value of x sub I should be? Yes.
It's like the summation of the I.
Yes. So since there's only two outcomes, you would multiply this value by the probability plus this value by the probability. This is 0. So the expected value of v sub I, x sub I, is vi over 2, right? Then maybe we can think about, for some subset of indices S, what would the expected value of X sub S be? Well, X sub S is the summation of the random variables X sub I's, where I is in S, right? And can someone tell me what's the next step? Yes. Yes, linearity of expectation. We love that. Yeah, so we can write this as a sum of the expected value of the xi's by linearity of expectation. And we know that this is v sub I divided by 2. So this is equal to 1/2 vi. This seems very familiar. Now, can someone give me an idea, which language do we want to reduce from?
Subset sum.
Yeah, exactly. This seems very much like subset sum. So that's what we're gonna do. Let's take subset sum and carve reduce it to RV. Again, we are given the sequence A sub I and then target T. We want to map it to the I's value R. I just rewrote it like this. Okay. I'll give you another 15 seconds to think about it. Okay. Would anyone like to volunteer an idea for reduction? Can we do the same thing? Can we maybe multiply 2 to all these numbers and do that? All right, let's go ahead and try. So for this one, the function f. So because there is a 1/2 factor here, and we want the expected value of x of I to equal to kind of R, which is our target for RV. And since there's a 1/2 factor, it seems like we want these values to be twice as big, but keep the target the same. So that if we calculate this value by summing up the values and then divide by half, we still get the original target, right? So the correct reduction for this is maybe multiplying 2 to each of these elements and then keeping t, the target, the same. Again, we can claim that this is polynomial time, right? Because they're multiplying 2 to each number, do that in polynomial time. Let's do the proof of correctness. Okay, first, let's assume our initial input is in subset sum. So there exists a subset of indices where the sum of AIs is equal to T. We can use that same subset of indices S because by math, we know that the 1/2 of the sum will equal to, oh yes. So what I want to say is, if we do this is equivalent. We multiplied each element by 2, but divided the entire sum by half, which is mathematically equivalent, and that's equal, should be still equal to our target T. Cool. And this is exactly our expected value for x of s. So this is equal to the expected value of x of s. So it follows that our transformation should be in RV. For the reverse direction, it is pretty much like the same thing. So let's briefly go over. Maybe you can assume that like there exists a, I'm doing option 1 here, such that like the expected value of x of s, which we define to be 1/2 the sum of the VIs to the target. Then again, like by math, this is equivalent to this, meaning our original input should be in subset sum. So and cool. Any questions about this? Yeah.
So you're saying that, for every x I, the I may not necessarily be the same as the different. So that if you have like x1 and x2, p1 and p2 may not be the same.
Well, what do you mean by that?
Like, in the definition of xi.
In this definition, yes.
Yeah.
Yeah.
So b1 and b2 can be different.
Yes, exactly.
Okay.
Yeah. So these random variables are all different, and they are each defined by like, I guess, what we feed in as like b1, b2, etc. Cool. Any other questions? Right.
I do the next one and then you do the last one.
Yeah.
I think I want to go in order of like difficulty to
Yeah.
some extent.
Sure,
I want to
sure.
do the hardest one last.
Okay.
Cool. Okay. Cool. So now we're gonna get some practice showing that stuff is NP complete also. And where's the, thank you. Okay, so we're gonna define the following language called click partition. Click partition is going to be the following language. It's asking, can we partition our graph into k disjoint clicks? So it's going to be G K such that there exists K1 of the K a subset of the vertices where the K i's are disjoint and the union of the K i's is equal to V or V. So we're trying to partition our graph into disjoint clicks and each Ki is a click. And we're gonna want to show this is NP complete. Yeah. So the two steps to showing that things are NP complete is what we always do this. If you see a question on the test, show this is NP complete. 1, proof that it's in NP. And so I'll walk through this part of the proof. And while I walk through this, I'll let you guys think about how to prove the complete the hardness. Yeah. Right. Yeah, I should specify that. Each Ki can have a different size, including 0. If we want a size 0 click, we can like just no vertices, that's okay. So if our graph, for example, if our graph is a click, then we can partition it into any number of clicks. Because we could just take the whole graph and then a bunch of like empty things. That's okay. Is that clear? That might be helpful in our proof that it's NP hard, maybe, depending on how we do it. Cool. So I'll walk through the proof that it's in NP, and while I do this, I encourage you guys to think about the proof of NP hardness, because that's normally the hard part of the problem. Okay, so proof that's in NP, we just want to come up with our verifier. So I input a graph and a number K and my certificate. And so I'll just spoil this because I want you guys to think about this. Our certificate should probably be the clicks that it partitions the graph into. So if U is not an encoding of K of K subsets of vertices in B, reject. And now I can go through and make sure these are disjoint for I, sorry, K, I, K, J pairs of click. So I'm just going through and checking each of these conditions. So if Ki intersects Kj is not empty, then they're not disjoint, so I reject. And then if the union of the Ki's is not equal to V, reject. If Ki is not a click, reject. Otherwise, I accept. I just stepped through the laundry list of things. So whenever you're like doing for the proof that's an NP, just step through the laundry list of things. Don't try to just do the laundry list. Okay. And now we can do the proof that it's a verifier. So it's polytime. Normally when I show things are polytime, I just go over here and I say like, this is like n squared, and this thing is like O of n or something, and this guy is like O of n, and this guy is like O of n squared. Just like yeah. The time complexities are often based on fives, but clearly these are polynomial time because like we're specifying at such a high level how these work that like clearly these can be done in polynomial time. So cool, we verified that. And now we can say by the exact same thing as always, we can prove it's correct. And then just step through the laundry list of things. And don't forget to show that the size of U is less than or equal to the size of it's polynomial in the size of X, which it should be because it's just a subset of the vertices, right? Or it's just like the partition of the vertices, which really should probably be like that. The size of U is just we like write out the vertices and what subset they're in. Cool. Okay. I'm not gonna go through this part. So now comes the fun part. It's NP hard. So does anyone have any ideas about what I might want to reduce to? I'll try. I have my idea, but I'm curious. This is like not an easy reduction. We're on to the adult reductions now. Does anyone have an idea? And if you don't say, actually, maybe I just say what I want to reduce it to, because I'm probably not gonna be able to figure out what you try to reduce it to, but maybe. If someone has, if anyone has any ideas. Otherwise, I'll say what I want to reduce it to. So. Okay, no takers. So what I want to reduce it to is 3 colors. Whoa, any 3 colors out there? Anyone? Yeah, okay. Okay, let's show that 3 coloring. It sounds like that was funny. Whoa. Okay, quick partition. Okay. I'll give you guys like a minute to think about how this might work. If anyone has an idea within the minute, let me know. It's okay if you're wrong. This is a supportive environment. There's no thing is wrong. This is incorrect sometimes. Oh, yeah.
What? Sorry. I'm sorry. Why can't we just reduce from
The issue with that is like so if the graph is a click, we can say like, oh, because we basically the issue is like the clicks here can have size 1 or they can have size 2 or anything. So whatever click partition tells us, like maybe there is a click in the graph, like there's like, some click size K over here. These guys are all connected. And then there's like more stuff. And I ask, is there a click partition of size 2? Like one of the clicks it give me could just be this edge. And then it could give me like a K-1 click or something.
Oh.
So yeah, I can't really like filter out. I don't know what it actually found, just that it found something. Yeah. But yeah, yes.
Could you, so if you could like partition this graph into 2 separate clicks, right? Could you color like one of those clicks like red and blue and the other one like red and yellow, so the whole graph is 3 colored?
So that's a good intuition. Which is it kind of feels like if I can like partition the graph based on colors, then that's kind of like a partition based on clicks. But then we run into the issue of like, so let's say the clicks I partition it into are let me do something a little more complicated. Let's just do wait a minute. Let's do this one. So this my fully connected graph. So if this is one of my clicks and this is another, and you're saying, oh, if I can partition it into like 2 clicks, I can color this one color and then that one another. But then we kind of run into the issue of like in a sense, like clicks are almost like the opposite of coloring. In the sense that like, if I have things in a click, they all need to be different colors, right? So like, if I know this is a click, I know it must be the case that like all of these must get different colors. And then like, I see like, oh, I have a 4 click, so actually I need like 4 different colors to make these guys. So there is like a nice correspondence between coloring and clicks. Does anyone see what that correspondence might be a little bit?
Reverse the graph, like if there are edges between 2 vertices, then there's no edge in the new graph. And
Right, okay.
if there is no edge, and then there's edge, and then it's like the independent set. So
Ooh.
so if there's K coloring, then you can partition the graph into K independent sets.
Yeah, so that's like a good observation, which was it almost feels like, given that we know that like there's some nice way to reduce 3 coloring the click partition, it feels like we want the clicks to correspond to the colors that we have, but then we kind of have the opposite problem, or like the problem where like a click is kind of the opposite of a 3 coloring. But the observation is that a 3 coloring is kind of like separating the graph into 3 independent sets in which there are no edges between any of those sets. And so the opposite of having, if I like take the negation of all the edges in the graph, that means I can find like 3 sets of the graph where they all have, like, every pair of vertices in them has edges. And so that's kind of the intuition, and let's like step through how this works. So the idea is we're given an instance of 3 coloring, so we're given a graph G. And our click partition is gonna, or so our answer result thing is going to be B comma E. We're gonna return return B, and then like how do I want to write this? Like opposite of edges. I can write this as like B times, no, I don't want to write it as B times B. Okay, let's make it B. Sorry, wait, there we go. This is how I want to write it. Oh my God, this is complicated. So I'm just, it's just the edges that are not in the original graph. Edges not in G. Okay, does anyone see any issues with what I just wrote? One thing is, click partition takes in a graph and a number. I didn't give it a number. Always remember, make sure all your things type check in the sense, okay, this is a graph and a number. What should my number be? 3, yeah, that's a good idea, because it's 3 coloring, so maybe 3 somewhere. Cool. So now the claim is that this algorithm, or like this mapping, is correct. So first I can say 1, it's poly time. Because all I do is reverse the edges. Cool. So now let's go about proving correctness. And it's a good thing to like have in the back of your mind, like these sort of like connections, right? Like if you ever see something about colorings and clicks, well, clicks are like the opposite of colors. So it's like the complement should come to mind, or like coloring an independent set. Like a coloring is or a coloring into K colors is like K independent sets. And if that's not super clear what that means, the proof of correctness should make it clear. So let's show that G is 3 colorable implies F of G is in click B. Okay, so let's just say G has 3 coloring. So let's call it like R, G, and B which are subsets of the vertices, right? With R intersect B is empty, R intersect G is empty, B right? A coloring is just we separate the vertices into like the red vertices, the green vertices, and the blue vertices. And there are no edges between any verts in the same set. Because that's what it means to be a coloring. Which what I'm saying is that like R is an independent set. B is, and G are they're all independent sets. That's like that's like the relationship between colorings and clicks. So now in the complement graph, so let's say F of G is equal to like G prime and 3, right? So in G prime, R is a click. So that means R, G, and B are all clicks. Right, just because I just reverse everything that had no edges is now all edges. So they partition and they partition G. And this is where it was important that like oh, I guess I erased the problem. I hope, do you guys all know what the problem was? Yeah.
You were first, one more.
Yeah, yeah. So we want to we're given a graph and a number K, and we want to split up the vertices into K disjoint sets. That account, like, we want to partition the vertices into K sets. Where, you know, every vertex is in one of the sets, and each set, no vertex is in two sets.
Okay.
And such that each set is a click. And it's okay if the clicks like connect to each other, right? So it's like, okay, if like, it's okay if this is our partition here with like 4 vertices. And so, because this is a click and this vertex here is a click, because we allow clicks of size 1 or size 0. Cool. So yeah, they partitioned G into 3, G prime into 3 sets, and yeah, it's a click partition. We happy with this? Cool. So now the reverse direction. I'll just write it as G prime 3 in click E implies G is in 3 color. Well, here, oh yeah, wait, what I was gonna say was that here is where it's important that we allow clicks of size 0. Because for example, in the graph that's 1 vertex, like this, let's color it red, then green and blue are both empty, but that's okay because we allow empty clicks. Because there's no vertices that are not that stuff. Cool. So here, if we're able to find 3 disjoint clicks in our like complement graph, so that means there exists, let me conveniently call them R, G, and B, subset B, E prime. Subset of B, such that all at that are clicks. So like negating the edges makes them have no edges. Also, can people still read the marker? It's kind of fading. Right, no complaints. So no edges. So it's a 3 color. 3 color, yay. All right, there's our proof of correctness for this. So is it clear why this kind of reduction works? And I guess like, I think on an exam, we wouldn't, I think it's like beyond exam difficulty to realize that like you should do 3 coloring because that's just gonna happen to work. But I think it's like pretty reasonable that like given that we could give you and like try to like do it from 3 coloring and then like figure out something like this. I would consider that as like reasonable but like difficult for exam. Maybe like a 10-pointer, maybe I'm I don't know. Yeah. But having in the back of your mind, and also this falls into the category of reductions where you do something to the entire graph or like the entire input, or for every input, you just like do the opposite. It falls into that type of reduction. Cool. Yeah.
You want me to do this?
Yeah. In particular, I think the last one is like easier. So
Yeah, let's go with it.
yeah.
Your brain's fried yet? Okay. Right. So we have 3 more questions left for you guys. 2 of them will be kind of more involved. So I'll start with kind of the easier one. Think of this as kind of your brain teaser or something as a warm up to the more difficult ones. Where's the blackboard thing?
You might want to switch to a different one.
Yeah, I have these, so we'll see. Okay, so yeah. Oh. Okay. Cool. So, you might recall we maybe slightly talked about like the problem Hamiltonian path. Have you heard it before? Yes, no, okay. And Hamiltonian cycle. Okay. I know there wasn't like homework questions on this, so maybe it's a bit unfamiliar. So let's go through like what these problems mean. So for both of them, like the input is a graph, undirected graph. So an example. Okay. I'll just label these A, B, C. Okay. And Hamiltonian path is ask the question like, does there exist a path that covers like all the vertices and each vertex only once, right? For this example, you can think of like a path starting at A, going to B, going to C, going to D. We covered all the vertices exactly once. And so this would be a Hamiltonian path. This would be a yes instance. Does that make sense? All right. How about like this graph like this? Is there a Hamiltonian path in this one? Yeah, I see heads shaking. No, because I guess no matter like where you start, you'll end up with a problem like you can't get to the last vertex. Cool. And then Hamiltonian cycle is kind of similar. You do want to like visit all the vertices like once, but for this one, you want to like come back to the original vertex that you started with. So if you have to take the same graph, there is no Hamiltonian cycle because if we try like going from A to B to C to D, well, we want to come back to A. So maybe a graph like this would be a good example because you can come back to A and there is a Hamiltonian cycle here. Make sense, everyone? Right. Okay. And as kind of a brain teaser, I guess, we'll be doing reductions from Hamiltonian path to Hamiltonian cycle and the other way around as well. Cool. Let's do the first direction. So I have this example graph before. We know there exists a Hamiltonian path from A to B to C to D. We want to transform this to another graph such that in that graph, there should be a Hamiltonian cycle. But we don't want it to be too loose in that like if there wasn't a Hamiltonian path before, we don't want our modified graph to have a Hamiltonian cycle all of a sudden, right? A good place to start with these kinds of reductions is kind of think about, copy the original graph and think about like what you can modify or add to this graph, right? You know there exists a Hamiltonian path from here, 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 here. Same for here, here to here, here. Okay. Now we need to think about like how can we transform this into a cycle? Yes, that's a great idea. Cool. So let me add a completely new vertex, call it X, and then I'll connect it to like all the original vertices in the graph. Would you agree that now there exists a Hamiltonian cycle in this new graph? We could just start at X, go to A, do our Hamiltonian path, and then of course we could come back to X again. Cool. All right. So I guess that would kind of correspond to the forward direction of the proof of correctness. And that if there was a Hamiltonian path, well, of course there is a Hamiltonian cycle. Now we also want to verify that the other direction is true. If there exists a Hamiltonian cycle here, it must have been that there is a Hamiltonian path in here. Does anyone have ideas about how we can make that argument? So if there was a Hamiltonian cycle in our modified graph, why it must have been the case that in our original graph, there was a Hamiltonian path to begin with.
Just say that if there's like a Hamiltonian cycle, that means that there is like a path that connects all of everything, because essentially the cycle is just a path, but it just like goes back.
Yes, so one thing about like paths or cycles, I mean, is that, so for this, like there's a cycle from A to B to C to D to X to A, right? But for a cycle, like it doesn't really matter like where you begin. You could say that it starts at B, goes to C, D, X, A, and comes back to B. But another thing you can say is like, oh, what if we started at X, we can go to A, B, C, D, and come back to X, right? It's a cycle. It doesn't matter where we start. So imagine as like, if there was a cycle in this graph, it must include the new vertex that we added, right? So there must have been a cycle like from X to like maybe vertex 1, vertex 2, all the way to like vertex n, and then back to X. So it must have mean that like if we look at the original graph without the X, well, just take this path right there as part of the kind of the subsection of the cycle. So so this implies that in our original graph, there should have been a Hamiltonian path. Any questions about that? Let's do the other directions. So now going from Hamiltonian cycle to Hamiltonian path. All right. Now this one's a little tricky. There is a Hamiltonian cycle in our original graph, and we want to transform it to a modified graph so that there is a Hamiltonian path. Well, if you consider just like the identity transformation, if there's a Hamiltonian cycle, well, then of course there is a Hamiltonian path, right? You just don't come back to the original vertex that you started with. But the problem is that like, if we use the identity mapping, if there is a Hamiltonian path, doesn't necessarily mean that original graph had a Hamiltonian cycle. So that's a problem. So we do need to modify this graph a little bit. Yes?
Can we like modify the pre-existing?
Sorry.
Can we modify the pre-existing cycle, or we can only like add stuff?
You can modify it. I guess maybe you can think about like, oh, what if like I removed like this
Yeah.
vertex or this edge? The problem with that is that, well, you don't know which edge that you should remove. Like, because then that would require you to know like which edges form the Hamiltonian cycle. So like, how do I know not to remove this edge? Right.
Do we add like a single vertex and a single edge,
To where?
like any vertex?
Any vertex. Okay, let's try that. Sure, okay. So if there was a Hamiltonian cycle in our original graph, well, in here, I guess we have to like start or end at this vertex. And then since there's a Hamiltonian cycle, we should be able to cover all the vertices. Let's think about the backward direction though. I believe it runs into the same issue where if you didn't have this edge, there still is a Hamiltonian path in this graph, but there wasn't a Hamiltonian cycle in our original graph. so we cannot necessarily do that. So it's a great idea though. In a way, by doing this, we force the Hamiltonian path to start or end at this vertex. So maybe what you can do is also have another constraint so that you get like both ends of the Hamiltonian path. So here is my proposed transformation. Okay, let me rewrite this here because one here. Okay. Okay, this is my original graph. What I'm gonna add is, let's just pick one vertex. I'm gonna add a copy of that vertex, A prime. And I'm going to connect this to, like if there was an edge between A and B, I'm gonna have an edge between A prime and B. Yeah. So all the vertices that A was connected to, I'm gonna connect that to A prime. In this case, it happens to be that A is connected to all the other vertices, so I did that, but if there was nothing here, then I wouldn't have an edge here as well. Let's actually just do that example. Okay, cool. And then, yeah, question?
Wait, does the other idea work if you have add two vertices to one vertex? Like, does it not force it to start there and like go back and then go to the other one?
But the thing about a Hamiltonian path is that you can't visit
Oh.
the same vertex twice. Yeah. So that's why, hence the new clone vertex that we added, A prime. And exactly, we're gonna follow your idea of forcing the cycle to, the path to start and end at some vertex. So let's add another vertex S for source, and then actually I wasn't sure where I was going with that, but okay. So now what's gonna happen is like we're gonna force the path to start at like either S or T. Let's just say S is going to A, and then if there is a Hamiltonian cycle in our original graph, we'll be able to cover all the other vertices, and then rather than like coming back to our original vertex A, we'll come back to its clone. And then we'll be able to go to the other endpoint. Does that make sense? So if there was a Hamiltonian cycle in our original graph, which is from here to here, sorry. Let's see that. We can go from S to A to B to C to D, but rather than go back to A, we go to A prime and then. Okay. So that, yeah, question. Yes, I believe so. That is because, let me think about that for a bit.
Like we did without the S&T kind of still have. You just expanded A and N though.
That is true, but I think the backward direction, there might be issues in the backward direction where let's see here, let's give an example. So if this was our original graph, and we added A prime like that.
But that could not be the original graph. You need to have like.
No, so I'm talking about the backward direction of proof of correctness. So it must have been that like, yeah, if there is a cycle, then our new graph should have a path. But it shouldn't be that if there wasn't a cycle to begin with, we don't create a path, right? So we need that to be true as well. So you're right. So your reduction does, if you didn't have the S&T, it does work in the forward direction. But I think my guess is that it won't work in the backward direction. Or if there wasn't a cycle to begin with, for example, in this instance, that is true. That is true.
You just add the vertex, you take a random vertex and then you clone it, so make a new vertex connected to whatever you're connected to. In each of your copies, you add another. Oh, yeah, vertex. That's so weird.
Yeah, I'll get back to you on that, but like, let's just assume that there we have S and T. The idea is that like we force like it to like start and end there. Okay, so for the backward proof of correctness, what we can argue is that if there is a Hamiltonian path, in this case, it is true. Remove like S and T from the path, and then since A prime was a clone of A, we can like merge this edge like back to A, and that forms a Hamiltonian cycle.
Yeah, that's such a good.
It doesn't work with just A prime on this.
Because like. the thing that-
If you only add, if this is your graph. And you pick this guy as your vertex A, then there's no Hamiltonian cycle here, but when you add the duplicate and then like connect it, there's a Hamiltonian cycle now, or a path now. Cause you go like boom, 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 like, so you introduce a Hamiltonian path when there wasn't a cycle originally.
All right, any questions?
So not
Yeah.
that.
Like, example.
Yeah. Yeah. Yes, so your reduction, your function f should work the same regardless of like whether the instance is in Hamiltonian path or not. So you're the same transformation. So you like arbitrarily pick one vertex to make a clone of, and then do that A prime, and then connect it to these, I guess, or not D. And then S and T again. But the idea is that if this was the case, there shouldn't be a Hamiltonian path in your new guys. No, that's not. What would your Hamiltonian path be? Or I was talking about the Hamiltonian cycle to Hamiltonian path reduction. So
It's you like, I don't even think it's not there's no way they like,
no, so the A prime thing was for the other direction of like reducing from Hamiltonian cycle to path. Okay.
So, just like, following it with the graph and it.
Cause then, like, they're not being, like, you can consider itself the entire graph. But like big partition, like it has to account for every single vertex. So you call it liquid fraction. If the entire graph is click, then it works. Otherwise, like there could be a click of size K, but you have to include every other vertex in like your partition. So you would have like every other vertex would add like another one. So that's like.
Oh, so if you the X is not as long as it knows where to see.
All right, let's
Yeah.
come back.
It's like, have edges.
We have some difficult problems to go through
We click to.
here. So for this problem, we're gonna introduce a new language called almost vertex covered. So for this problem, you're given a graph. And number K, like usual. And if we want to see if there exists some subset of the vertices of size less than or equal to K. And if there exists a subset of the edges as well, such that the size is exactly 1 minus E, meaning T contains all the edges except one edge. Okay, such that for all edges in or subset T, E is incident to a vertex in S. This is kind of long, so let's unpack this. What this means is that we want to come up with a vertex cover, so some subset of vertices, right? So that we cover the edges in the graph. But we relax it a little bit in that we can have an almost cover, in that we can miss exactly one vertex, one edge, excuse me, out of all the possible edges. So in the regular vertex cover problem, we wanted to cover all the possible edges in the graph. For this problem, we allow it to miss at most one edge. For example, if this was our graph, in regular vertex cover, you couldn't say like, let's just pick this guy as our vertex cover because you miss this edge right here, right? But for almost vertex cover, let's count this because it's almost there, like it's missing one edge. So this would be a yes instance of the almost vertex cover problem. Does that make sense? All right. And we want to show that almost vertex cover is NP complete. Let's quickly run through the proof that this is in NP first. So we're going to define a verifier taking in the problem instance and also a proof string U. Right. First thing we do, we want to check like if U is of format, of some format that we want. When you think about like what the proof string should represent, a good thing to think about is like, if I'm given this problem instance, what would help me to like solve this problem? Like what would be the answer to this problem so that I can verify it and confirm that it's correct? In this case, the problem is like, does there exist a vertex cover that like covers all the edges except one? I would claim that if you told me the vertices in that set S, and also the one vertex that you choose to like not cover, then I'll be able to verify that you have the correct solution. So let's just say that if U happens to be an encoding of the set S, and let's call this some like edge E star. So it's some reasonable encoding of a subset of vertices and one edge. So if U is not of this form, then like we reject right away. So we're dealing with U that are encodings of set S and one edge. So to verify that this is correct, what we need to do is that confirm that every edge is covered except E prime. So for all edges E in our graph G, if E happens to be E star, which is the edge that we chose to like not cover, then it's fine. We like continue. Otherwise, let's say like E is between some vertices U and V. Let's confirm that like either U or V is in S. Check that. Sorry, this is kind of messy notation, but just want to check that either U or V is in the subset S. And then if not, we can reject. If all the checks pass at the end, we will accept. Cool. Does that make sense to everyone? Right. So like quickly, this should run in polynomial time because we're just going through all the edges. So maybe I would say like, oh, this thing like O of M stuff and checking this is maybe at most like O of N. So in total, it should be still polynomial time. Cool. In terms of correctness, you can do your kind of basic thing that we always do. Yeah, I guess Harrison went over this, so I won't go over this for this problem. Cool. All right. Now the hard part is showing. Marker's kind of thin. Let's show that almost vertex cover is NP hard. It kind of gives it away, but what might be a good language we want to reduce from? Vertex cover, yeah. Vertex cover. All right. So how are we gonna go about this? So if this was our original graph, actually, let me go back to the example that I had before. Yes. My example and k equals 2. Is there a vertex cover of size 2 in this graph? Yes or no? Thumbs up is yes, thumbs down is no. Yes. We can do this one, size 2, and then it covers all the edges. Okay. Now, how can we map this to a different graph? Like I said before, like a helpful thing to start with is like the original graph itself. Maybe we can do some modifications or additions to this. Okay. Yes?
Can you choose a random edge and then like add a vertex between them that connects the two edges and then remove the original?
So like maybe pick this one and then replace it with a vertex. And what would that do?
Then what vertex?
That is a good idea. But again, with strategies where you like have to pick a edge and it depends on that edge, whether like the reduction works or not, might not be a good idea, right? In this case, like, I guess it works. But maybe like the vertex or the edge that you picked was this one. And you do this, and there'll still be a, I guess in this case, like k equals 2 will still work. So maybe if this was like, okay, sorry, but like basically the idea is like, your reduction depends on like which edge that we choose to modify. That makes sense. So what we want to do is it'd be nice if you could control the edge that we choose to like not be part of the almost vertex scope. What I mean by that is, okay, any ideas? Oh, yeah. Yes, that would be a good. So add 2 new vertices, like we want V2, and then just add an edge between those 2. Okay, so now for the proof of correctness. The forward direction, I'm gonna skip over because it's pretty straightforward, right? If there was a vertex cover in the original graph, we can keep the same vertex cover, and the only edge missing will be the new edge that we added, right? Okay, let's look at the backward direction though. So I'm going to pick the option where you assume that our modified graph is in almost vertex cover. Then we want to get to that the original graph was in vertex cover to begin with. So if our modified graph is in almost vertex cover, that means there exists some subset of vertices S of size at most k, such that S covers all edges but one. Let's call that E or E star. Now the thing is that like we don't necessarily know like which edge it chose to like not count. And like we don't know like specifically like which vertices are part of this vertex cover. So what we can case on is if V1 or V2 is included in S, and our case 2 will be like S is strictly comes from our original graph. Do those cases make sense? Let me start with if S was a subset of our original set of vertices B. So this was our original graph, it would be E, and let's call our new graph B prime, E prime. Okay. If this was the case, then we can, the edge between B1 and B2, you know that like this vertex cover can't cover this edge, right? Because all the vertices are coming from this part. So that means this is the E star edge that we chose to like not cover. That means all the edges in our original graph must have been covered by this vertex cover S, meaning we keep the same S, and S is a valid vertex cover of our original graph G in that case. That makes sense? Right. Now we have case 2. If either V1 or V2, the new vertices that we added, happen to be in our almost vertex cover. Well, then we can't go about it the same way, because if V1 or V2 is in S, then this edge was the edge that was like covered. So that means like the E prime must have come from the original graph, and maybe like there exists some E prime, maybe it's this one that we forgot, that we chose not to cover. To prove this, I will claim that let me okay. We consider this new set S, where we remove vertex V1 or V2. So we're looking at S prime, which purely comes from here. My claim is that in the original graph, S prime covers at most S prime does not cover at least 2 edges in our original graph G. Or in it doesn't, there are at least 2 edges that it doesn't cover, is what I mean. So yes. Yeah. That's because, so what I mean by that, sorry, for the confusion, but if we took S and then we removed like V1 and V2 from it, well, then that means this edge is not covered. And also there must be an edge here that is not covered, right? So there are like at least 2 edges that are not covered, right? Okay, so that means that there exists an edge in original graph that was not covered by S, namely this edge in this case. Cool. So yeah, okay. And note that the size of S is strictly less than K, right? Sorry,
There's actually 2 edges. Because they cover one edge.
Yes, it's true. Yeah. Well, then my conclusion is that like the original graph should have
Yeah, so you're missing one edge in the graph and you took away one vertex on the right. Or maybe one or two vertices.
All right. Oh, yeah, yes, sorry. Okay, so. So since we took away like at least one vertex from S to create S prime, we can, and there's at most like one edge that we are missing from the original graph. We add this, add one of the endpoints back, we get a, I guess, new vertex cover, which is strictly fits at size bounds, it's less than or equal to K, and it covers all the edges in the graph. So in our original graph, S double prime should be a valid vertex cover. Of the original graph G. Okay, sorry about the confusion. Yeah, just explain this one more time. For case 2, if it happened to be that our almost vertex cover contains one of the vertices that we added newly, that means there's at least one edge that's not covered in our original graph. And there's at most one edge that's not covered in our original graph. So we can remove the vertex that we have, either whether that be V1 or V2, and then add one of the endpoints of the edge that we're missing. Then we'll get exactly a vertex cover for the original graph. All right, sorry about that.
All right, now we have one last problem for you guys. I'll try to get this done by like 4. But yeah, okay. One last problem. This one will have the flavor of we're gonna show something is NP hard, and there's an obvious thing we want to reduce it to, but I'm gonna tell you you can't reduce it to that. So we're gonna define sub 3, the problem sub 3 color, which is equal to a graph and a number, and it's asking, does there exist a subgraph of G with K vertices that is 3 colorable? So when I say a subgraph, I mean, like if this is my original graph, these guys, and I select these 3 vertices, then my new graph would just be like, I remove all the edges that I keep all the edges between those vertices, and I remove all the vertices and edges that like were not incident to them. And for example, I would be allowed to select like, this as my subgraph. Like if they don't need to, they don't need to be connected. And our goal is gonna show that 3 coloring is NP hard by I wrote it the wrong way. By reducing independent set to 3 coloring. So the obvious thing that I would want to reduce this to is 3 coloring and just ask, can I 3 color the entire graph? But we're going to want to show that independent set is reduces to 3 coloring. So what I'm going to want to do is define my mapping function that takes in graph and a number, and I want to answer, does there exist, and just a reminder, does exist K vertices in G with no edges? Okay, so does anyone have any ideas for something I might want to try? It's okay there might be issues. This is a kind of difficult one. And so my reduction will probably have the flavor of like do blah for like every blah in the graph or something of that nature, right?
Would you add two other vertices to each vertex?
Okay, so do something like if I have like my original graph, then for every vertex I like add two vertices and then do what? Yeah, so this is a good first thing to investigate. Because the idea is with three color ability, like if we have a triangle, we know that every vertex in the triangle will need a different color, right? So if I have, but so then this will run into like a slight issue where so it kind of feels like, okay, if I have a triangle, every color needs to be used in this triangle once, right? So I'll have RGB here. And now the hope is that if I have two triangles that are like next to each other, like I don't want to be able to pick like two vertices that are next to each other, right? But one issue that might arise is, for example, I can like color this guy like this. Like something like this, where this graph is actually three colorable. But like, so this graph is three colorable, like the entire thing. So somehow I need to make sure, and I guess this set only has an independent, or this graph would only have an independent set of like size 0 or size 1. So does anyone have any ideas of like how I can modify this to maybe?
No vertices and connect the two vertices to connect each of the two vertices to all the vertices in the graph and also connect the two new vertices together.
That is a good idea. That's not what I had in mind, but I like this idea. Let's see. And then what would we do? What would we do? Because
So if it has an independent set, we can color all the vertices in one color, but we create two new vertices and each new vertices connect with all, so it's
that is a good idea.
each vertex is like a vertex of a triangle.
Yeah. Let me think of that's not what I had in mind, but I think that works and is simpler than what I had in mind. So let's see it. Let's think about if this and then so I guess the idea is we're gonna like return so okay, so I think this okay, wait, that means so I guess that means we're not if we're not gonna add triangles like this. We're going to add two new vertices here and connect them to, we're basically gonna make a ton of triangles with these guys. Oh wait, let me use different colors. I believe this is gonna work. Let's find out. So the idea is we need to color these two vertices. Okay, wait, no, actually, I think this will not work because we have no way of enforcing that we actually pick these two new vertices in our like, so there will, for example, there will, like, I can three color like three guys over here. Like I can just pick like three color this part of the graph. So there's actually, I think, yeah, I think something like this wouldn't work because we can't enforce that we actually pick these vertices. Okay, wait, I see that it is 4 o'clock, so I'm gonna speed run a little bit. So let's go back to the idea of triangles. And just look at, let's see what happens if Okay, so this was my original graph G and I just added triangles. Let's look at what happens if I connect like each triangle to each other. So if I just connect every vertex in each triangle to like every other vertex in each triangle. And this quickly becomes like a mess and kind of hard to reason about. But the idea is, and there are more edges, but there are more edges that I'm not drawing. But the idea is, so for each vertex in the vertex set, add two new vertices, B1, B2, or yeah, B prime, B double prime, make a triangle with B, and then for each edge U, B in the graph, connect all pairs in like U prime, U double prime, B prime, B double prime. So I'm making triangles for every vertice, for every vertex, and then connecting all of the vertices in every neighboring triangle together. And so I guess like some motivation behind this is now it's kind of like if I have two, so let's look at what happens now. If I look at like two triangles, if these triangles are next to each other, I can include at most 3 vertices from the triangles in my like 3 coloring graph. So what I mean by this is let's look at a subgraph of this guy. And I'm just like, a subgraph is going to be, I pick some number of vertices, right? So let's say these two guys neighbor each other. So I'm gonna pick this vertex, this vertex, this vertex. All of these vertices are connected to each other. So each of these vertices will need a different color, right? But the moment I add a 4th vertex from these 2 triangles, this is no longer 3 colorable. The graph I get from doing this. Because if I add 4 vertices, all these 4 vertices here are all like connected to each other. So each of them will need a different color. So this will not be, this subgraph is not 3 colorable. Is this clear? That like with this strategy, I can only pick 3 vertices from like any pair of neighboring, at most 3 vertices from any pair of neighboring triangles that I create. So with this idea in mind, I claim the reduction of like return like this called this guy that I get down here, G prime, and then 3K. And so this this problem is kind of a doozy because there's kind of a lot going on here. But if we believe that like making triangles for every vertex and then connecting these neighboring triangles together has the property that I can select at most 3 vertices for any triangle, then we can kind of go on to the proof of correctness for that. This is a harder than exam difficulty problem. But let me walk through the proof of correctness. I think this is a cool one because there's like a little thing that comes up in the proof of correctness that doesn't normally come up in these sorts of fields. So let's show that if GK is in an independent set, then f of G is in sub 3 col. So if there's an independent set of size K, I could just pick like all the triangles I make from those guys, right? So I'll just take subgraph of like V prime, V double prime for each V in my independent set. Right? Because I know that like if 2 vertices are not connected to each other, then none of the vertices in their triangles will connect to each other. So I've just found 3K vertices where none of them connect, or like where I can like three color, all of them. Cause they either like have the thing where I can like color their triangles independently, or like the triangles don't overlap at all, so. Yeah, if you have questions about this, you can ask after, I don't wanna keep people here too long. Okay, and now we can show the backwards direction, which is that if f of g is in sub 3 col, then GK is an independent set. So my goal is to find an independent set of size K, given I know there's a subgraph that I can color with 3K vertices. And what's kind of weird about this is that actually, I don't know of a way to be able to like find an independent set of size K given that. But what I can do is show that one must exist. So my goal is to show that that there will exist K vertices in the original graph G with no edges between them. And here is where I can use my observation that any pair of neighboring triangles can have at most 3 vertices in them. So if f of g is sub 3 colorable, then I know any pair of neighboring triangles can have at most 3 vertices in a 3 colorable subgraph. And so what that tells me is that I must touch at least K non-neighboring triangles. Which is my independent set. Because for any triangle, what I'll take is just the vertex in the original graph that was in that triangle. And that, ladies and gentlemen, is this very complicated problem that I didn't have enough time to do. But if you have questions about this, you can come up and ask. But otherwise, have a lovely Sunday. Good luck on the